It's a pleasure to have you back at the school. For those of you who were not at the poster session yesterday, my name is Hitesh Changlani. I'm an assistant professor at Florida State and National High Magnetic Field Lab. Yeah, so on day one, we had many body localization. On day two, we had hydrodynamics, and now we are switching gears to Floquet Systems. And our first speaker is Professor Rodrick Moessner. Really needs no introduction, but I'll say a couple of lines about him. So Rodrick did his PhD with John Chalker and was sort of a pioneer, I would say, in frustrated magnets, working on pyrochlore systems. Went on to do a postdoc with Shivaji Sondhi at Princeton, and also collaborated with many others. And is very famous, very well known for spin ice and discovery of magnetic monopoles in pyrochlore systems. And over the last decade or so, if I may say, he has kind of switched gears while also being very active in frustrated magnetism, to working on non-equilibrium dynamics, non-equilibrium systems, Floquet systems. And also is very famous for his work on time crystals with Vedika Khemani and again Shivaji Sondhi. He's going to tell us a lot more about it today. And with that, the floor is yours, Rodrick. You have time till 11:30 local time. So, so that's a 1.5 hour lecture. The format is going to be similar. Would you like interruptions, frequent interruptions, or should I look at questions in the chat? What would you prefer? Rodrick, there? We cannot hear you if you are there.
Okay, can you hear me now?
Yeah, I just wanted to ask you, would you like me to assemble questions in the chat and ask you, or would
yes,
you like
please. Yeah, okay, yeah. So please listen, please, if you have any questions, either interrupt me or just write something in the chat, in which case Hitesh will have to pick up on it because I can't actually see the chat.
That's okay. That's fine.
Okay.
Okay. So thank you, and go ahead. Please go ahead.
Good. So thank you very much. So first of all, to Kun Yang and Hitesh for doing all the hard work in the organization, and for getting all the technology. And as he just said, so I'm suffering from the delusion that I've got enough time to cover the entire material in my talk. So really do stop me whenever things are going too fast. This is quite important because I'm trying to essentially get you from the very basics of the problem to the experiment that happened last year. And it would be nice if you could follow all of this. So please stop me if there's any problems. Okay, so here I'm giving two review papers. So the first one is a very short review as the basic theoretical work on understanding what happens to thermodynamics and order in the Floquet setting had appeared. And then the other review, which we entitled A Brief History of Time Crystals, goes into much more detail. And so I encourage you to have a look at that if you want to really fill in some of the gaps that I'll have to leave in the presentation. So a little bit of history about this winter school. So when Hitesh and Kun Yang asked me whether I'd like to co-organize this, I was very keen on this. And my main motivation was that I'd be in Florida and actually meet a new generation of young scientists in the field. So as you can see, the main motivation for my doing this has essentially disappeared. But I nonetheless like to welcome everyone, and I really hope that we will be able to meet, because one of the things about the lockdown, of course, has been that everyone has their network of people they know and they collaborate with, but you don't meet new people, and I think that's what I'm really lacking. And so I'd really like to encourage you to show up and talk to me at some point. And in fact, let me just see, there was a summer school which we planned for 2020, which then got moved to 2021 and now 2022. So this is with the people listed here. So we still hope that this will be an in-person event at the end of the summer, which has been the best time for traveling pandemic-wise recently. It's got quite a high overlap with what we want to do here. So it's a 3-week summer school And if any of you are interested in attending that, please do apply. And as I said, it would be really nice if we could have in-person events again. And I'm pretty optimistic that one's going to take off. Okay, so I'm going to be relatively brief on the very, very basics, basically because Anusha gave an introduction to these things. But let me just start in the 19th century. This starts with equilibrium thermodynamics, and the basic underpinnings are things which are so obvious that we hardly ever formulate them, and these are equilibration and thermalization. And you heard a detailed introduction to this, but basically the ideas are, so first of all, large systems. There's someone typing, could you perhaps stop, mute yourself? Okay. That large systems eventually reach a steady state. That's equilibration, and thermalization means that this steady state depends only on very few parameters, like energy and particle density. And so this photograph really captures this. So basically, if you see this picture and you think, okay, what's going to look like when you come back after an hour, you don't expect it to look like this anymore, but you expect it either to look like a puddle of water or like many little ice crystals. And so these are these two ideas. So equilibration, you come back, eventually the system reaches a steady state. And thermalization, that if I tell you what the temperature of this photograph is, then you will know what the steady state is going to look like. And this is something, as I said, that holds as a matter of course, but it doesn't hold always. And one of the questions is, why does it hold? So this was what Anusha talked about. And what happens if it doesn't? And this is what I'm going to cover in a very limited way today. Okay, so eigenstate formalization was covered. So let me just on this one slide say, so this is now the 20th century. So we've moved from the idea of equilibrium thermodynamics to the idea of a closed quantum system. And this is a huge, huge jump because the closed quantum system is determined by the Schrödinger equation, which has wave functions which live in a very, very high dimensional space. We no longer have a bath, which we normally assume to be present in equilibrium thermodynamics. So it's really completely different. The question is, what is the connection between the two? We know that, or we expect that there should be a connection because the quantum world is described by equilibrium thermodynamics in most respects. And so the basic idea that you heard about eigenstate formalization is simply that I do not, in fact, need to give you the solution of the Schrödinger equation to have an eigenstate in which I evaluate an observable, but rather that if I give you a quantum state at a given energy, its observable is basically going to be fixed simply by the energy at which you're sitting, and it's not going to depend on the details of the eigenstate you're looking at. So whether you're looking at the 1/1,000,000th or the 1/1,000,000th first eigenstate isn't going to make a big difference. In other words, observables are a smooth function of the energy of the eigenstate, and you don't need to have all this spectacularly detailed information of the eigenfunction of the eigenstate. So that's eigenstate formalization. Okay. But the question I'm going to address today is what happens beyond equilibrium. So this was equilibrium thermodynamics, its connection to quantum mechanics. Now I'm going to ask what happens beyond equilibrium, and what can we learn about sort of about quantum dynamics outside equilibrium. Okay, and this, as you may imagine, is a huge field. So non-equilibrium situations, in fact, are the norm. So if you just look out of the window, you will quickly recognize that the system is not in equilibrium. And I'm not going to give you a fully general description of non-equilibrium physics. So in other words, by the time anyone can explain how a coral reef comes about in microscopic detail, I think none of us is in this world anymore. So we have to take, as always in physics, a much more modest aim. And this is to go to a simple setting where you go away from equilibrium, but not too much, in the hope of carrying over some of the concepts of equilibrium thermodynamics and then extending them into a realm which wasn't available before. And much of this has happened of late. So for a long time, there are some fairly well understood systems like lasers, the X-ray edge problems. And there's been a lot of work on quenches and equilibration physics. Fabian Essler covered some of this in his talk. But I'm going to focus on a combination of two things. So one is driven systems, so where the system is not in equilibrium because you keep perturbing it. And another one is many-body localization, where the system is not in equilibrium because it doesn't manage to reach equilibrium. And I'm going to show how these act together to give you new physics. Okay, so what is the simple setup that I'm thinking of? So the simple setup I'm thinking of is a periodically driven system. So this is motivated in part because it's a common non-equilibrium problem. So if you shine a laser on something, then you have a sinusoidal perturbation or sinusoidal variation of due to the finite wavelength of the laser, or many problems in real life are approximately periodic, such as tides or the rotation of the Earth and things like that. And so it's a common problem, and it's only a weak perturbation away from the completely static case, as I'll make more precise in the next few slides. So then the question is, what is the fate of thermodynamics? So first of all, are there still some concepts from thermodynamics which I can borrow, which are going to give me something like an ensemble in this periodically driven realm? And the second question is there still a notion of phase structure? So is there still a notion of disordered phases and of ordered phases, and of phase transitions between them? And these are the two problems, the two issues I'm going to address in turn. Okay, so to be at least concrete about what we're talking about, so we've got a non-stationary Hamiltonian, which is periodic with period t. And that means if you Fourier transform this, you only have frequencies which are commensurate with the basic driving frequency omega, which is 2 pi over t. Okay. Right. And so now for describing this, many people find it useful, so many people, including myself, to define what's called a Floquet Hamiltonian. And this is here a completely formal definition. We basically say if I evolve any initial state over a period t, this is like, it's unitary evolution. So so basically I can have my basis of states. I can ask, what do they look like after time t? And this evolution is encoded by the time evolution operator denoted as u here. So formally, so this is the middle part of the equation, I basically integrate up the Schrödinger equation from time 0 to time capital T. And this then gives me a big unitary time evolution matrix over one period. And then I simply decide to call, so this is purely definition, the logarithm of that time evolution operator I call the Floquet Hamiltonian. Okay, and even though this is called a Floquet Hamiltonian, it's in some ways like a Hamiltonian, in other ways it's not. So in particular, even if your Hamiltonian H is local at any given point in time, generally the Floquet Hamiltonian is not going to be local. But one of the reasons it's useful is that since U is a unitary matrix, so since U is a unitary matrix, it still has a system, an eigensystem, which of orthogonal vectors which forms a complete basis. That is to say, the idea that you've got a complete set of basis states is true both for a periodically driven system and for a static system. So even though the Hamiltonian is no longer local, you still have a complete set of states about which, eigenstates about which you can ask questions.
Rodrick,
Okay,
can I ask a question?
Yeah, sure.
Yeah, does the proof of this Floquet theorem, does it just come from Dyson series expansion? Like, how do I prove that there is a Floquet Hamiltonian, which is a Hermitian?
Okay, so
if it's Hermitian, then of course it's as a complete, but.
That's right. So since it's a unitary matrix, since the time evolution at any given point, so the instantaneous time evolution is unitary, okay, and therefore it remains unitary for all times.
It's some sort of discrete definition that whatever the unitary is, then then
that's right. That's right. So it really is a definition. I mean, the unitary is really the basic thing, and the Floquet Hamiltonian is what you decide to extract from it.
Okay, I get it. Thank you.
Okay, and the quasi-energy conservation is going to come out because the logarithm isn't single valued. Generally, because you can add 2 pi times I and get back where you started.
Correct.
From. But I'll come to that in a second. Okay, that was the first thing. You've got a Floquet Hamiltonian, which has a complete set of eigenstates. And the other thing is that you no longer equilibrate. As I said, you don't equilibrate because you keep kicking the system periodically. But what you can still do is look at always the same time within a period. So this is what's called stroboscopically. and then ask whether the stroboscopic series of observations converges to a time-independent limit. So if it becomes constant at long times, you call this a synchronized state. So for a driven system, the generalization of the equilibrated state is the synchronized state. And we're going to look at the properties of the synchronized state here, provided it exists. And one of the central results towards the very end is going to be in a time crystal, there's actually no synchronized state by this definition. And that's very special. Okay, but this is really the main thing. So we have the unitary, which defines the Floquet Hamiltonian, and we've got the synchronized state. Okay, now let me say something about the general sort of mental attitude behind what I'm going to say for the rest of the talk. So it's a closed system. So we're going to look at model Hamiltonians, and only I think once or twice I'm going to specify the precise Hamiltonian we're looking at. But all the Hamiltonians that I'm going to look at have the following properties. So we're looking at a closed system, so there's no dissipation present. We look at a lattice system in one dimension for mainly technical reasons, even though not all the results that I'm going to display carry over to high dimensions. And we look at a lattice system with a finite dimensional local Hilbert space so that we've got a bounded energy density. So in other words, the system can't just absorb an infinite amount of energy at some point. There's as much energy in there as you can, and that energy is finite. So these could be fermions, these could be hardcore bosons, or it could be spin systems at finite spin length S. The Hamiltonian is going to consist of static and time-dependent terms, but all the time-dependent terms are periodic with period t. And we're going to assume in some places that their amplitude is actually small. But again, not always. Okay, so if you want to, depending on which community you come from, you can think of this either as a like called atomic particle system, where there's a random potential or a potential in black, particles density n, which can hop with matrix element T and interact with matrix element V. Or alternatively, you can think of it as a spin system, where a particle present is a spin up, particle absent is a spin down. XY exchange has strength T, and Ising exchange has strength V. And these are completely equivalent. Now, the basic attitude I'd like you to take is that I can't give you any universal results, or only a few universal results, because we don't really understand things in enough detail that we can really make these universality statements. But what I'd like to argue is that most of what I'm going to say is generic. That is to say, there are large families of Hamiltonians which behave in the way that I'm going to be advertising here. It's not a complete classification. So if you show up and tell me, okay, here's a Hamiltonian which behaves differently, I'm not going to be shocked, but I'm going to be pleasantly surprised. But I still think that if you come up with a random Hamiltonian, chances are it's going to be behaving like one of the cases I'm going to describe in the following.
Rodrick, there's a question in the chat. I think it's a very good one. That if you're driving the system, technically it's not a closed system anymore. So is your definition of closed that there's no energy losses then? That's the question.
Well, no, there is. And I mean, driving means that you can put energy into and out of the system. I mean, so I think the statement is that there's no dissipation and no bath. So basically, I'm giving you alternatively, I'm giving you a fully unitary time evolution with a Hamiltonian which happens to be time dependent. Right, so this is not like one of these non-Hermitian descriptions where part of your, where you have photons leaking out of your system, but there is a fully unitary time evolution, and there's no Lindblad operators, blah blah blah, none of this. Right.
Yeah.
So
hopefully the person who asked the question, Nancy, hopefully that answers. Okay. Yeah. Great.
Right. So I mean, so let me perhaps, we can discuss this in the end, because this is, this can take us quite a long way. Now, it's a little bit like the question, even if you're doing equilibrium thermodynamics, you still have to plug in your magnet and your and your refrigerator. So what is a closed and what an open system is something, in actual lab detail is a complex question. So this is not trivial, but the statement that this is a unitary time evolution is a very sharp description of what I'm doing. Okay, I hope this answers the question. Okay, so the next slide is one that I found useful when I got into the field, and you don't need to absorb this for any of what follows, but I found the intuition behind it very useful. So you can, if you have time periodicity, you can make an analogy to spatial periodicity. So you know that real space is homogeneous and invariant under infinitesimal translations. But in a crystal, when you break translational symmetry, you still have discrete spatial translations. And so this is like periodic driving, where you replace the continuous time translation symmetry by discrete time translation symmetry. And then you can make an analogy. So like in a crystal, so here I'm showing you, say, a photon, which has a linear dispersion. But once you break the translational symmetry, you replace momentum conservation by crystal momentum conservation. So momentum is only conserved modulo 2 pi over a, where a is the lattice constant. And then, but this is just a way of bookkeeping, you know, even if you have no periodic potential, you can still decide, okay, I'm doing the bookkeeping modulo with a lattice constant a, and then this gives you this band folding so that the dispersion, which would have continued here, actually just gets folded by a reciprocal lattice vector. But then when there are degeneracy points and you've got this periodic potential due to the lattice, you actually lift this degeneracy and you mix the two branches. So you mix the right moving and the left moving branch, and you end up with a band gap here. Okay, so I hope you're familiar with this physics, but I'm going to now make an analogy later what happens in time periodic systems, where something like this happens in energy space. But you should basically remember that band folding is basically like stroboscopy. So it's like periodicity in space and periodicity in time. And the gap opening is going to turn into level mixing, as I show in a second. What is sort of different, just not conceptually, but in practice, is that when you're driving a system, often it's very easy to change the frequency of the drive. Whereas in a lattice, typically it's not so easy to change the frequency, the wavelength of the lattice, because that's spontaneously generated by some symmetry breaking. So one way you can think of the non-conservation of energy is that you can say, well, if the energy is not conserved modulo 2 pi over t, I can basically take my energy axis and say, okay, if 2 points in the energy axis differ by h bar omega, then I'm going to identify them, which means I'm taking a straight line and I'm turning it into a circle. So if I'm driving very fast, then the frequency is high and the circle has a big radius. And if I'm driving very slow, then the frequency is low, the radius is small, and I'm folding this into a small circle. And then say if my system has a certain bandwidth and energy, then either the two edges of the circle overlap, in which case I can have resonant energy of the photon, because I can take this state and excite it here. And if they don't, then it's like this, and the photon basically is mismatched. And this is going to play a role later when we talk about many-body localization. But anyway, so think of this analogy, and there's this tunable sort of radius of the energy axis in the Floquet setting. Okay, so I'm going to give you two pictures of what happens to eigenstate formalization in Floquet systems. So one very important difference, thing that happens between a static and a Floquet system is that in a static system, the energy is extensive. So if you have a system which is twice as long, then the highest energy and the lowest energy are both doubled. But by contrast, since the driving frequency omega is independent of system size, this extensive axis, energy axis in the static system, gets folded onto a radius of a circle with a radius which is independent of system size. And this has a number of consequences, and one of them is that the relative location of the states, the red energy is bigger than the blue energy, is not going to remain after you folded it. So the quasar energy in blue may be higher than the quasar energy in red. And states which may be very far from each other, like the green and the yellow one here, may actually end up folded on top of each other. Right? So this is like the band folding. Okay, and now if you switch on the driving, what happens is the following. So we've taken states from all over the spectrum and put them together here. So this is just the span folding, and now I'm switching on the periodic driving on the x-axis. So basically, I've got so each little point here is the quasi-energy of an eigenstate. And then you see, as you switch on the perturbation, you just mix all of these states together. So the same way that you mix the states here with a periodic potential in real space, the driving potential mixes the eigenstates which have been folded from the static case. And you see, as you increase the driving strength, you just get one level crossing after the other. And so I'm just taking whatever the 10th state in red here, and I'm following through it. And if you want to go back and ask, where does the amplitude from this state come from? You can basically follow all the other level crossings. And what you find that it comes from a very big region of the original energy space. Okay, so what this is supposed to motivate is that the quasi-energy is only very weakly related to the original energy of the static Hamiltonian of the states that it consists of. Okay, and this is basically supposed to motivate the result, which I'm going to derive differently on the next slide, that you lose any concept of high and low energy in this in periodically driven systems. There's an even simpler way of seeing this, which is in the time domain, which basically says, look, you've got the different states here. This is the static system. Now imagine you start driving them by switching on your drive so that the system can absorb photons of the drive. So it's often useful to think of the drive as sort of, as sort of a laser, as a laser acting on your system. And then, but there are many more states going up in with high. So if you start with a low energy state, there are many more states going up in energy than down in energy, because the highest density of states is actually essentially at infinite temperature or at zero net energy. So let me just say this a little bit more slowly. So imagine you're sitting at low energy. So then you're subject to driving, and if you say, okay, the probability of making a transition is basically given by how many states I have access to, then there are more states at higher energies than at low energies. So that's the same as saying there's a bigger entropy at high energies than at low energies. And actually what I'm plotting here is the energy on one axis and the entropy, the logarithm of the density of states in the other. So all I'm saying is, if you drive the system, it absorbs photon to go to the high entropy state until finally it reaches the maximum. Then it's balanced between absorbing energy and releasing energy. Okay, and this then tells you, okay, in the end, I'm going to sit at infinite temperature, so that there's going to be essentially, the system is going to be saturated with energy. So this is the same as saying here, you know, there is, no matter where I start, in the end, each eigenstate I have actually is comprised of states coming from all over the original axis. Okay, yet another way of saying this is to say, well, I've told you the energy axis essentially becomes a circle. In a circle, there's no concept of high and low anymore. Yeah, it's just rotation invariant. And so in other words, the quasi-energy is periodic. And if you say Eigenstate Formalization tells me that the observable is a smooth function of energy, that's then what's the simplest smooth function on a structureless circle? Well, it's a constant. So in other words, if I want to take this Eigenstate Formalization picture where I've got an energy and an observable, and I now plot it, an observable versus the quasi-energy, then I get this picture here. Here's the quasi-energy, here's the observable, and it's completely constant. So that's the statement about Floquet Eigenstate Formalization.
Sorry, I have a question. Is it because the Floquet Hamiltonian is non-local? I mean, how did that factor?
And I'll come to that in a second. Yeah. Okay, so you need a non-local Hamiltonian. Okay, but this is the central result. If you keep Eigenstate Formalization in the Floquet setting, it tells you that there's no non-trivial structure. So this is what we have here. So the question, what happens to thermodynamics in generic many-body system, is it suffers a heat death and you have no non-trivial correlations. In particular, you have no order. Okay, so yet another way of seeing this, and this is the final one, I promise, is like in equilibrium thermodynamics, you maximize entropy. If you don't have any constraints, not even energy conservation, then you get Floquet ETH. So if you don't have energy conservation, so if you have energy conservation, this allows you to define a temperature. Here you don't have energy conservation, therefore you don't have a temperature. So Floquet ETH means you don't have a concept of temperature, all the states have trivial correlations. Okay, if that were all, then I'd be done now, and wouldn't have anything to talk about in the next hour. But of course, there is something else, and I'm going to talk to you about two different things. So one is transient phenomena. So basically, even though Floquet ETH eventually happens, there may be something which happens on the way. It's the first part of the remainder of the talk, and the second part of the remainder of the talk is that we're going to look for other sources of constraints to replace energy conservation. And then we're going to see what happens as a result. Okay, so are there any questions so far about Floquet ETH? So Floquet ETH in many ways is the most fundamental, even though slightly boring result. And I mean, you may be amused to hear that even though the questions that were being asked could have been asked way back in whatever 1940 or 1950, but Floquet ETH wasn't discovered until 2014. And when we worked this out, I was quite shocked that no one in these 70 years had actually bothered to work this out because it was not that difficult. Okay, are there any questions? No? Okay, so let me go to the transient phenomena.
I have a question.
Yeah, okay.
So you mentioned there's no bath in this Floquet system. So, and there's no definition of temperature. Then how do you define thermalization?
Okay, I guess what I'm saying is that instead of equilibration, you look at synchronization, and the synchronized state has no structure. So once you reach a state with no structure, you can say you've thermalized to infinite temperature. This is then a question of words. The precise statements is you have a state, the density matrix of which is like the unit matrix, right? So that's what I'd call. Sorry, if you have every eigenstate. Okay, so no matter which state you start from, so you basically do a quantum quench in such a Floquet system. Eventually, you reach the state which has no non-trivial correlations. So that's what I'd call. Well, that's what you can call thermalization. Does that answer the question?
Thank you.
Okay. Okay, so let's look at let's start with transient phenomena.
Any other questions? Okay, let's proceed.
Another question? Okay, so the universal physics that we learn most of the time in condensed matter and many body courses happens at long times and distances. And if you ask what happens at short times and short distances, then sort of the generic answer is, well, anything can happen. There's no universal principles other than that you have to obey causality, Robinson bounds and so on, and that if you can't have transitions which are symmetry forbidden and so on and so forth. But basically, it's a little bit like asking what happens out of equilibrium. Really, just about anything can happen. Even coral reefs can happen. But it would be nice to be a little bit more specific. Just because anything can happen, you can still ask, well, under what conditions do things typically? What are typical results given a set of typical conditions or generic assumptions? And I'm going to give you two aspects of this. So one is pre-thermalization. So basically there's an idea that you can have a parametrically long-lived regime before you heat up to infinite temperature. And another one, which is closely related, is called Floquet Engineering. And I'm going to include this because it's very important in practice. Based on a Magnus expansion, I'm going to first cover Floquet Engineering, and then I'm going to tell you how this is related to pre-thermalization before I then move on to what happens before I then move on to the question, what happens beyond these transient times. Okay, for those of you who haven't seen Magnus expansions, this may be a bit much to digest in real time, but conceptually it's very simple. So if you've got a time evolution over one period, as we had a few slides back, when Hitesh asked his question, you can define a Floquet Hamiltonian. So basically, you've got the time evolution operator over one period, which is a unitary matrix. You get it via a time-ordered exponential, and you use this to define via taking a logarithm the Floquet Hamiltonian. So then if you drive your system very fast so that the driving period is very small, you can use the driving period t as a small parameter. So again, this is completely formal. You write your Floquet Hamiltonian as a sum Taylor expression, as a sum from m equals 0 to infinity of the period t to the m times some operator omega m. Okay, and if you do this, then what you find, and again, this is just formal manipulations. The 0th order t to the 0 bit is just the average Hamiltonian. So it literally is the average Hamiltonian, no time ordering or anything like this. The first term in the, so the 0th term is the average Hamiltonian. The first term is just the integral of the commutator of the Hamiltonian at 2 different times over the times. Okay, and then if you go to higher order, omega m's, you just get increasingly long, complex nested commutators. But we're only going to be using these two in what follows. So it basically, so the totally stupid observation, if you drive extremely fast, all you see is the average is encoded in the 0th order term, the 1st order term. It basically is, if everything commuted in your Hamiltonian, obviously the eigenbasis would be time independent, and you could simply add up the phases that accumulate, and something non-trivial only happens if the Hamiltonian doesn't commute at different times, which is why in the Magnus expansion, the non-trivial business only happens if you've got a non-zero commutator between the Hamiltonian and itself at different times.
There is a question about the Magnus expansion, if I may ask. In the chat, is it related to the BCH expansion? Is the Magnus expansion just time-dependent BCH expansion?
I mean, these are related because you're basically taking you're taking an exponential and writing it, decomposing it by taking the integral and splitting it over independent exponentials. Yes, so it is the same algebra that you do. Yeah.
I have a question.
Yeah.
When you say rapid driving, and t is a small parameter, you mean t is smaller than what?
Okay, so I was a bit sloppy because I didn't want to write down a precise Hamiltonian here. So if you've got a lattice system like I described with a finite Hilbert space, then you write down the Hamiltonian. It's got hopping terms, interaction terms, and so you just take the biggest of those, and you say, or you take the sum of those or whatever, and then you say, so this is your unit of energy, and then 2 pi over t is your unit of frequency, and you basically say that 2 pi over t is much bigger than any of the terms appearing in your Hamiltonian. Or you can take the local energy bandwidth and say this is the typical size of my local Hamiltonian, and then you compare 2 pi over t to that. That's what it means. Okay, so answer the question.
Okay, thank you. Yeah.
Okay, so now let's do Floquet engineering. So the idea of Floquet engineering is basically the following. You would like to realize a Hamiltonian H effective, which has some specific properties that you want, but you can't realize this directly. You can only have access to some other Hamiltonians like H static and H drive, as I'm calling them. You can also call them H1 and H2 or whatever. But let's assume that you've got a static Hamiltonian, which you can't do anything about. That's just given by the material that you have. And then you've got a drive Hamiltonian, which you can do something about, and you want to do something clever to the drive Hamiltonian in order to get the effective Hamiltonian. And so what Floquet engineering does, it chooses a driving protocol to generate an appropriate omega 1, so this correction here, so that omega 0 plus omega 1, the new H effective, is the one you want. Okay, I'm going to give you a concrete example, which is 35 years old, the first case of Floquet engineering I'm aware of, even though as far as Floquet engineering goes, it's something pretty dumb. But I think as a matter of principle, it shows what you want to do. So imagine you've got a particle hopping on a chain, so hopping matrix element J. So it's not called T as normally in many body physics because T is already the time. So J, A dagger A, between side I and side I plus 1. And what you can drive is an electric field, So this is just the density at site I times I. So the potential of a uniform electric field is proportional to the space index I. So E of t is the time-dependent strength of the electric field, and the potential that comes out of that is just I times the number density at site I. Okay, and then you can work out the commutator between H static and H drive is just another hopping term. And this is just 2 lines of algebra. Work out the commutator. And then you need to do this integral. And when you do the integral, what you find is that you get a hopping, that you can, by choosing the E and the frequency appropriately, you can actually exactly cancel out this hopping term here. So in other words, if you had wanted to stop your particles from hopping, you could have done this by driving with a uniform electric field. Okay, so, and then you find that this, the destruction of the hopping actually only occurs at isolated driving strengths E. So in other words, you can, for a given frequency, you can vary your driving strength continuously, and every once in a while you find that the effective Hamiltonian exactly vanishes and your particle no longer hops away from where it's where you put it in the beginning. So this is called dynamical localization, and this and its generalizations has been quite important over the years. But it's important to realize that we're using a separation of energy scales, and it's not true to say that the particle is entirely stationary. But what is true is that if you look at a time scale which is much bigger than the driving period, then the particle doesn't move. On the time scale of a driving period, it does what's called micromotion. So it does move around, driven by the electric field, which moves, which goes backwards and forwards very fast, but it does so in a way that after a period, it's back to where it started from. So if we go back to the synchronization picture, it literally does something like this. So after a period, you're back to where you started from. So you say, fine, the particle doesn't move at all, but actually in between it can move. But stroboscopically it doesn't. Okay, so this is the first thing, so this notion of micromotion. So Floquet Engineering, so of course here's an extremely simple case, but has been fabulously important because there's many things that you can do, like in cold atomic systems, where again, you have access to certain types of static Hamiltonians and certain types of drive Hamiltonians. You can then try to Floquet engineer a Hamiltonian of interest. So one prominent example is that if you've got a ferromagnetic system of cold atoms, if you shake the lattice in a clever way, you can change the sign of the exchange constant and generate a frustrated or an antiferromagnetic interaction, which say on a Kagome lattice is then frustrated. So that's one application of this. Another application, I think, which was mentioned yesterday, is Floquet topological insulators. I think that was mentioned in one of the posters. So basically, you take graphene and you drive it with a rotating electric field. And as Takashi Oka and Oki showed, if you do this, you open a gap and you get a topological insulator, which is topologically non-trivial, even though all you're doing is taking a system which is topologically trivial and just putting a circulating electric field on top of it. Another application, which I think was also mentioned in one of the posters yesterday, was that you can generate effective spin interactions between trapped ions. So imagine you've got 2 trapped ions a certain distance away from each other, then and you'd like them to interact. Then even if they don't have an electric field which via which they interact, if you do something clever to the vibrations that they experience, and you apply spatially dependent laser fields on them, you can actually introduce quantum gates for quantum computers. So this goes way beyond what I'm covering here, but if anyone wants to know in a bit more detail how this works, I can describe that in the questions at the end of the talk. Okay, so but that's basically the idea of Floquet engineering. So by using the Magnus expansion, you can get a Hamiltonian, which is unlike both the static and the driven Hamiltonian. The effective Hamiltonian has properties that you find useful. Okay, so where's the drawback? The drawback is eventually you heat up the system. So that's the content of Floquet ETH. You can do all these clever things, but the system in the end keeps absorbing photons and then heats up. And this can be a big problem in practice. So for 2 reasons. So one is eventually it happens. So this limits the time over which you can do this without cooling your system. But in condensed matter physics, it's sort of for an even deeper reason, or even more fundamental reason, I'd like to say, it's a problem, and that's the following. So normally our Hamiltonians in condensed matter physics are low energy Hamiltonians. So, there's low energy space, say, in a mod insulator, we have a Nail antiferromagnet at half filling. And so we have a spin Hamiltonian, which is a Heisenberg Hamiltonian, which defines our low energy space. And then there's a Hubbard gap, so the size U, and then there are all these doublons, holes, and so on, and you get a much more complicated itinerant system up there. So if you now say, okay, I'm driving with frequency omega, and I'm just making this omega very large, then what you're going to do, is not just dress your state like you want to do here, but you're actually going to create you're going to resonantly create lots of doublons and holes in your system, and then the system just is going to heat up very rapidly because you resonantly do this. So if you have an isolated atom, this problem isn't so big because there's a big mismatch in energy scales and there are not that many states up here. But in a many body system, this is a real problem, and especially if there isn't a gap between your low energy description that you're interested in and the higher energy states, there may not be any window where you can actually do a Floquet driving like this. So this is just worth bearing in mind. And so then this brings us to the question, okay, if we have this short time description of the Magnus expansion, what happens on the way to Floquet ETH at infinite temperature? Okay. Whoops. And so this is what's known as Floquet pre-thermalization. So here's a nice review on this topic from which I've taken this figure. So basically the idea is the following. So if the heating time that you have is very, very long compared to all the microscopic times of your static Hamiltonian, then it may be that the time evolution isn't just you start from the initial state in a quench and then you go to infinite temperature down here, but it may be that there's an intermediate plateau before the heating really sets in, where you've got a non-trivial description, which is different both from the starting state of the quench and the long time infinite temperature state. And so this is now connected to what Hitesh was saying. So for Floquet ETH, the Magnus expansion actually is not convergent. And the reason you see it's not convergent basically is this. If you work out, if you've got local Hamiltonians H, and you just work out their commutators like this, it's always going to remain a local Hamiltonian. I mean, the range is going to grow with your order M because as you take commutators, the support of your operators can grow, but it can only grow to include the terms which were present here in the non-commuting terms in the Hamiltonian. And so since each of these was local, their composite is also local. Okay, but now what I'm saying is basically, if you look at the eigensystem of the Floquet ETH system, you have no non-trivial correlations. And so the only way that you can do this basically is if you're you can do this is if your Floquet Hamiltonian is non-local in the end, right? Because otherwise you would basically still be able to tell the states apart from each other locally. Okay.
Excuse me.
Yeah.
Yeah. By local, do you mean local in time domain or something else?
I mean spatially local. So okay, so this is an important point. So look at the drive here was literally on site, and the hopping is nearest neighbor. So if you work out the commutator between those, it's only going to include, after you take the commutator, it's only going to include indices I plus 1 and I, because the AI here doesn't commute without AI, but you're still only going to have operators of support too. But if you have next nearest neighbor hopping, you can get something slightly more complicated, but you can never get indices appearing in these commutators which weren't there in the original Hamiltonian. So in other words, if these only have supports on 1 or 2 sites, then at nth order, you're not going to have suddenly support on 10,000 sites. It's going to be at most sort of 2 times n sites or something like this. Does that answer the question?
Yes, thank you.
Okay, Great. Okay, so one of the nice things about pre-thermalization is that there exist some rigorous results, which I'm going to appeal to now. So you can basically read this paper and find out how they are proved. So the downside on rigorous results often is that they're not physically particularly transparent, and the upside is you're at least sure that they're absolutely correct. And so I'm just going to cite that result, which is that, so the Magnus expansion is not convergent, but it's nonetheless useful. So we have many of these non-convergent, but nonetheless useful series in many body physics. So these are known as asymptotic expansions. So these are expansions where the first few low orders actually give you an increasingly good description of the system. But then after some while, if you add further orders, it's not that your description gets better, it's actually that it gets worse. Okay, and in such asymptotic series, the challenge is to essentially identify the ideal order up to which your description gets better and after which it gets worse. And what you can show in the Floquet systems is that the optimal order to which you want to go is basically the inverse of the period of your drive times this typical energy scale that was explained in response to the question in what units you measure the time. So in other words, the faster you drive, the higher the order until which your Magnus expansion is useful. And then you can show that the resulting error in the observables grows linearly, is bounded in a way that's linear in time and exponential in 1 over the temperature. Exponential in 1 over the period. So in other words, if you say I'm happy with an error of a particular size, then you can run this for a time which is at least as big as the pre-thermal time, which goes up exponentially with 1 over your driving period. So in other words, the faster you drive, the longer this pre-thermal time persists, and the longer, by this I mean it actually grows exponentially fast. So there can be a very wide window for experiment if you drive fast enough. Okay, and so this is the idea of pre-thermalization. So even though at long times you get killed by Floquet ETH, by heating to Floquet ETH, there can nonetheless be a very wide window for experiments in which you can observe the H effective. And this is then what underpins Floquet engineering. There is a sufficiently large window in which your system is described by H effective. And this is pre-thermalization. So in some sense, Floquet engineering is one of the simplest applications of pre-thermalization. And you can generalize, okay, so this is the central result here. You can generalize this to other conserved quantities. So if you've got some symmetries, so even if you start with a state which doesn't have a thermal expectation value, which corresponds to infinite temperature, but it has some conserved quantity, which is not trivial, then you can have a similar picture where you first equilibrate within the sector of that particular value for the conserved quantity, and until such time that the conserved quantity also relaxes to its the approximately conserved quantity also relaxes to its infinite time limit. Okay, so that's
I have a question.
Yeah.
So you are using powers of t to the 0, t to the 1, and so on. Is there a way of not using polynomials of t, but some other functions? I mean, you just have instead of using a power series, can you use some other series of t?
Yeah, do you mean like Chebyshev type things?
Yeah, that's what we do in. That's one question. And the second question is, what if you're slightly off perfect periodicity? Like, does this picture sort of survive, or does it? Does heating happen much more quickly, or is there some stability in some sense too?
I think that depends on which phenomenon you're looking at. I mean, things like the time crystal, which I'm going to come to later, eventually dies if you have a slight offset there. But so if you have a drive which isn't perfectly periodic, then you have to basically ask, what is the spectral decomposition of the drive?
Right.
And then it depends on, what
does the sublead?
Yeah, so it's how does the density of how does the spectral density vanish as you go to small frequencies. That plays a big role. But also, are there, do you have considerable spectral density at frequencies corresponding to particular transitions in your many body systems? So I think generally I can't answer that question other than saying,
sure,
if you do this, if you do this, you have another channel for, ruining things. But I have some examples for different families of drives, but I'm not sure. So there are some families of drives,
now,
for
we
instance.
can talk about it later. Sure.
Okay. Where for instance, the exponential gets replaced by a power law. That's the kind of thing that can typically happen. Okay, good.
Question? Can I ask one more question?
Yeah,
just
go ahead.
Here is this statement true only if we truncate at order M0. If I truncate at some other order, do I have similar results?
So I think you can have similar results. The quality of your bound is going to change, right? So you can truncate after the first order, and this is going to give you a bound which looks worse than this one.
Yeah, and
right? If you
suppose I want to get this exponential error, I have to truncate at this M0 order.
So first of all, it's M0 is of order 1 over JT. So of course you can truncate at M0 over 2 at 2 times M0. But I think that if you if you truncate at order 1 over JT squared, or 1 over square root of JT, you're going to get different bounds which are going to be worse. Right. So that's the thing about bounds. You can always prove a worse bound, right? But I think the claim is that within this framework, within this proof framework, this is the best you can do. It doesn't mean that you saturate the bound. There's numerics which suggest that actually this is the bound, that this is the behavior. But you can always be lucky and actually have a pre-thermal regime which lives much longer, right? So this is just the bound that you're guaranteed that the pre-thermal regime will live at least as long as this.
So if my Hamiltonian is kind of random, so I have a distribution of J, what does this 1 over JT mean?
Oh, then it would just, so depending on the probability distribution, as long as it's a sufficiently narrow probability distribution, it's probably the mean. I couldn't tell you what happens. You've got broadest probability distributions, whether you then have to take the maximum or some moment or something like that.
Okay.
Right, but I expect it to be just the order, a typical J. Now, again, since this is a proportionality, factor of 2 or 3 doesn't change the argument. The functional form remains the same. There may be some prefactors which are suboptimal, but that doesn't make a difference. Okay. All right, good. So let me skip the Floquet integrable systems. The only thing I wanted to say following on from yesterday. So this was the transients. So now I'm going to ask about long times. What I've basically said is that if you drive very fast, you almost conserve energy and then you get pre-thermalization. And the fact that you don't conserve energy at all means that in long time you've got Floquet ETH. So underlying this is the idea, if you've got a conservation law like energy, you can define something like temperature. And then this temperature labels your, say, thermal density matrix or something like this. So the idea now in an integrable system is that you've got many conservation laws. This is what Fabian Esler was explaining yesterday, and you can do exactly the same argument. You've got many conservation laws, you get many Lagrange multipliers. And so basically, rather than having one temperature, you have many Lagrange multipliers going along with each of the conservation laws. And then the same way that the temperature is something you can tune, now it's the Lagrange multipliers of these conservation laws that you can tune. And the cool thing is you can also do this in periodic systems. I'm not going to go into details and just say they're also integrable periodic systems. And these integrable periodic systems then have ensembles which look like the Gibbs ensemble, except for instead of temperature, you have the Lagrange multipliers going with these conserved quantities. But that's it. So basically, the structure in thermodynamics is due to conservation laws. If we lose energy conservation, we can replace it by something else. And the main part of the remainder of the last third of the talk now is to replace the conservation laws by the L bits of many body localization. Okay, so Anusha gave you an introduction to many-body localization. So here's just the one slide summary for the purposes of what we're going to need. So Eigenstate Formalization was observable as a function of energy is a smooth function. So as function of energy of an eigenstate is a smooth function. So each of these points is an eigenstate. They're ordered by the energy and you get the smooth function. If you do the same thing in a many-body localized system, you don't get this, you get what's known as Eigenstate Chaos. So basically, if I'm sitting at one state and I just go a little bit away in energy, the observable may change by a lot. And if I want to go to a state which is the same, which has the same observable, then I may have to go a larger distance in energy. Okay, so I can explain how this comes about if you like, but since there was already a lecture on this, I think all you should really take away from this is that there is many-body localization. Many-body localization can be understood in terms of L-bits. That is to say, it's almost a classical picture where you say the disorder is so strong that I can say, okay, my eigenstate is essentially labeled by, is there a particle in this site or is there no particle in this site? And then for a generic many-body localized system, the actual observable isn't whether there's a particle here, but it spreads over a few lattice constants, but basically there's a local, almost classical observable, which the L-bit, which you can use to label things. So what I'm going to do in the following is pretend that these L-bits are actually local sort of Ising spins, and then use that as a picture so that you can think of essentially classical pictures and what follows. Always bearing in mind that the quantum dynamics is considerably more complex, but this is sort of under the hood. Okay, so now let me discuss what happens to many-body localization in Floquet systems. And so here we return to the picture we had earlier on, and this is now extremely simple. So imagine you've got a chain of length L, and very roughly, the statement about localization is that if I do something at one part of the chain, then what happens at a distance several localization lengths further away is basically not affected by this. So this is the information about the perturbation is localized around here. Okay, so in other words, I can think of cutting the chain into bits which are much bigger than the localization length and not too much should change. If I do this and look at one of these bits, this is now, even though it may be long, it's now a finite length system, and that means its energy, the total energy between the highest possible energy state and the lowest possible energy state is finite. And in the sense sort of a Magnus expansion, I can now ask, am I driving very fast compared to this energy difference, or am I driving slow compared to this energy difference? So if I'm driving very fast, so that the photons I'm driving with is much bigger than the energy difference between the highest and the lowest state of this cut chain, then I can't absorb a photon, and it's basically as if I were not driving at all. Whereas if I drive slowly, then I can induce transitions and the system is going to heat up. So the prediction basically is for fast driving, the system is not going to be absorbing any energy and many-body localization survives. Whereas for slow driving, I can have resonant heating and the system heats up to Floquet NBL. So this is shown here as a particular cold atomic system as before, quasi energy here, observable there. For fast driving, you get this many-body chaos. For Eigenstate Chaos, for slow driving, you get this Floquet ETH, where the observable is trivial. Okay, and so in other words, the phase diagram for strong disorder, you've got localization. For weak disorder, you've got ETH. If you drive very fast, you have the static transition, and if you drive very slow, then ETH wins at the expense of MBL. I should say it's not entirely settled, as I'm sure Anusha mentioned, where this phase transition is. In particular, not everyone agrees whether it happens at finite disorder or infinite disorder, but basically this is the picture. If there is many-body localization transition at a finite disorder, it's going to be stable to drive. Okay, so in other words, we can take many-body localization and the L bits and transpose them, import them into the Floquet setting. Okay, so next thing I'd like to introduce is eigenstate order. Actually, I did want to ask, did Anusha cover eigenstate order or not?
Is there a question
I don't
for
think
me?
so. No,
Okay.
I don't think she mentioned it at all. No.
Okay, so let me explain what eigenstate order is. So this is going to be a detour into completely standard classical stat mix. So I hope, so for those of you who know it, you can switch off for a couple of minutes. For those who don't, this may be useful. Okay, so if you have an Ising ferromagnet, transverse field Ising ferromagnet, you know that the two ground states are either all spins point up or all spins point down. But the actual eigenstates for a finite size system are not those, but rather they're cat states up plus down or up minus down. And then you can ask, what is the splitting between those two? And the splitting between those two is given by the size of the matrix element connecting this state to that state. So then what is the size of that matrix element? Well, you have to flip all the spins. So you have to do high order perturbation theory. You first flip one spin that generates a domain wall at cost j, and it's got a matrix element gamma. Then you flip the next one. You still have an excited state with one domain wall. Therefore, it's got energy gamma, and again the hop. It's got energy cost j, the exchange energy, and the hop again has matrix element gamma. And you have to hop this this domain wall for L order L's hops, so that you've flipped all the spins. So that's basically this thing. You flip the first one, then you flip the second one, the third one, the fourth one, and so on, until you finally get there. So each intermediate state comes with an energy denominator J. There's always a matrix element gamma. There are order L of those. So the energy difference is actually exponentially small in the length of the system. So you've got your two Schrödinger cats, and they're exponentially close to each other. This is different in excited states, because if you look at the multiplet of excited states with one domain wall, then you do degenerate perturbation theory, and to hop the domain wall from here to there has matrix element gamma, but there's no energy denominator. Therefore, the energy is just basically gamma cosine k. That's just a hopping problem in one dimension. And that means that the energy splitting within this manifold is algebraically small. It's gamma over L squared. So in a clean system, you have a doubly degenerate, quasi-degenerate ground state, exponentially split ground state, and then you've got algebraically split excited states. But in a disordered system, this is different. And the reason this is different in a disordered system is because you don't do degenerate perturbation theory. The energy cost of the domain wall depends on the local value of J. If this local value of J is not uniform, then basically if you want to hop the domain wall from this location to that location, from this location to that location, you have a lot of intermediate states with the energy of which differs by order J. And therefore, you again have an energy splitting between these different Ising reverse states, which is exponentially small in the system size. Okay, and this is what's known as eigenspectrum order. I'm going to explain. This is the basis of eigenstate order. Basically, that not just in the ground state, but in a disordered system, also in the excited states, do you have these doublets of Ising symmetry-related states. Okay,
Excuse
so
me.
yeah.
So the disorder mentioned here, is it the same disorder as you mentioned previous slide, where you discussed the phase diagram of MBL? Yes.
That's right. Yeah, that's right. So it would be disorder saying Jij. That's right. So, okay, I mean, you can disorder both the transverse field, but here the important thing was the disorder in Jij, so that the energy of the domain wall depends on where it sits, so that you don't do degenerate, so that these states are not all degenerate. Okay.
Mm-hmm.
All right, so basically, so there's the normal splitting of the ground state, cat state splitting, but the cats are also split the same way for the excited state. So in other words, if you're sitting in the paramagnet where you don't have the Ising reversed, so now, if you have a transverse field and an exchange, I'm going to show this in a bit more detail a couple of slides further on. But if you're in the state, if you're in the phase where the strongest terms are the exchanges, then the eigenstates are approximately labeled by the directions of the spins here in this L-bit sense. And then these two states, ground states, have an exponentially small splitting, but the excited states also have an exponentially small splitting, and they come in pairs. So this is what's known as eigenstate order or eigenspectrum order. Whereas if you didn't have this kind of double degeneracy, you wouldn't have the cats, and all the states would be isolated like this, and they wouldn't have such a nice pairing property. Now, this idea of using quasi-degeneracies to diagnose order is quite old. So for the Ising, if you do exact diagonalization on an Ising system, quantum Ising system, this is actually how you look for Ising symmetry breaking. You look at the splitting as a function of system size of the low-lying doublet. But it was also, like in 1989, I think, proposed by Zhaogang Wen as a form of topological order. So even if you don't have a local order parameter, in the Laughlin state of the fractional quantum Hall effect, you get a triply degenerate ground state reflecting the threefold degeneracy of the Laughlin state at nu equals a third. To have this order, to have this degeneracy also at higher energies requires many-body localization. So the first ingredient that we had was many-body localization is stable to Floquet systems, and the second one, many-body localization, enables you to have this eigenstate order at finite energies. And then you can see where this is going. Is there a Floquet version? So the quasi-energy is periodic now, so there no longer is an idea of a lowest lying singlet. But if there's eigenstate order throughout the entire spectrum, you can also have that in the Floquet setting. So there's a distinction between the non-eigenstate ordered paramagnet and the eigenstate ordered ferromagnet or spin glass. And so this is what I'm going to come to next, an actual example of this, but this is what we're looking for, pairing of eigenstates. So let's look at a concrete Hamiltonian and Ising chain. So there's a spatially dependent value of the exchange J. And then, so transverse field has now morphed into H rather than gamma. So sigma X is the quantization axis of the field, and H is, Z is the direction of the transverse field. And this is just to break integrability. You can basically ignore this, even though if you do exact diagonalizations, it's important. So what we're going to look at is the spin glass order parameter, chi, and which basically, so this is known as an Edwards-Anderson order parameter. And basically, if you have a random sign of J, and if you look at a correlator between spins sides I and J a very long distance away from each other, it can be zero for two reasons. One reason it can be zero is because every individual pair actually has a big correlator. But if you average over different pairs, since these big correlators come alternatingly with plus and minus sign, the average may be zero. But the other reason that the correlator may be zero is simply because each individual pair has a zero correlator, as would be the case in a paramagnet, where two spins at long distances are not correlated with each other. So the way you get rid of this problem is you square the correlator before taking the average, because then a negative and a positive large correlation is going to both turn into a large positive correlation. Then you can average and get a non-zero value in the ordered phase, or in the spin glass phase. And so we do this here. Oh, whoops, sorry. So this is the axis where the field dominates on this side and the exchange dominates on that side. And what you see is that this Edwards-Anderson spin glass order parameter vanishes when the field dominates, so when the spins just point along the field, whereas it saturates when the exchange dominates. So if J is very large and the field is very small, this is essentially classical spin glass, and the eigenstates are simply given by different configurations of the spins in the X spaces. So you basically see that in a Floquet system, so this is a driven system, you can still distinguish a paramagnet from a spin glass. And there's a phase transition between the two. So in other words, once you have many-body localization, you get rid of Floquet ETH. Floquet ETH in itself doesn't allow for any order because all correlations are trivial, but MBL and Floquet together give you the opportunity of actually having a spin glass phase which is separate from a paramagnet. And so without this integrability breaking term, this problem is exactly soluble. And you can then look at the phase diagram and you can take your values of J and H in a way that puts you in different parts of this phase diagram. And I'm going to show you now what happens when you perturb these bits with this term here. So we're going to look at this Hamiltonian numerically in different places in the phase diagram, and this is what we find. So we want to look directly for eigenstate order. So the way we do this is we take our periodically driven system. We diagonalize it completely so that we get the eigenstates phi alpha and phi beta for different quasi energies alpha and beta. Then we take some operator which doesn't commute with a Hamiltonian, and we look at the overlap between the two as a function of the quasi energy difference between alpha and beta, between states alpha and beta. And if you do this, you can tune your system across a phase transition. Again, the details don't matter. As I mentioned, there is a phase transition which you can diagnose here. So if you're sitting on one side of the phase transition, A of omega is basically flat. But if you're sitting at the ordered side of the spin glass side of the phase transition, A of omega becomes very large at one particular frequency, which is 0. That is to say, if you've got a state, eigenstate, quasi-energy E alpha, then there's a strongly enhanced probability to find another state at eigenenergy, at the same eigenstate energy, quasi-energy, whereas in the disordered phase, there's no preference and there's basically no pretty much uniform probability of having this operator connect those two states. Okay, so this is direct diagnostic of eigenstate order. Now, here's the cool thing. You can do the same thing for different parameter values. And then what you find is the same plot, except for now the eigenstate energy difference is not 0 as it was before, but pi over t. So remember, energy is conserved modulo 2 pi. So this is half of this, right? So in other words, if the 0 spin glass would be the same as the 2 pi spin glass in this language, but here we've got what we call the pi spin glass. And pictorially, if you just go back to the eigenstate order picture here, right, there was the circle, and then there were little circle of quasi energies, and then the states, each state at a given quasi energy was denoted with a line here, and eigenstate order was that the lines come in pairs, and no eigenstate order was that they come in singly. And what we find here is that the eigenstates still come in pairs, but they now come in diametrically opposite pairs, because the as the radius here is 2 pi over t, so diametrically opposed is an energy difference pi over t, which is just this here. So you immediately see that this is a new type of order, right? Because it really has the driving frequency, that is to say the circumference of the circle in the definition of the eigenstate order. So whereas this one basically has a static limit, you basically just make the circle bigger and bigger and bigger, but the states stay close to each other. This one doesn't, because if you make the circle bigger and bigger and bigger as you go towards the static case, then the energy difference between the quasi-energies grows and grows and grows as well. Okay, so this is really completely different, and I'm going to discuss the properties of this particular state in the next remaining quarter of an hour of my talk. Okay, are there any questions about this? Yeah. Mm-hmm.
Sorry, there's a question in the chat. I think it's related to what you just said about the pairing. Somebody asked, is it somehow related to pi modes? Maybe they can unmute and ask more. Yeah.
If I've got time in the end, I'll explain the connection, right?
Okay.
So in the non-interacting problem, the difference between the two cat states is the occupancy of the pi mode. So if you know what, presumably the person asking that question knows what this is, so that should answer the question, I hope. And if I have time, I'll come to that, although it doesn't really look like it, but I'll be happy to answer these questions afterwards. Okay, so here is now the central phenomenological slide. So I've told you we've got pi eigenstate order. How can I understand this in a pictorial way? And so here is that. So we've got a simple case of an easing magnet, which has an easing order parameter, which basically tells you the difference between up and down. So these are related by an easing symmetry. And so semi-classically, okay, and so then the eigenstates, as we said, are up, plus, and minus down. So this was the argument earlier that you've got matrix elements and so on. And now you can imagine taking this compass needle literally and just watching it in a sort of semi-classically as it rotates over a period. And then there are two options after a period is that either the state comes back to itself, that is to say, the compass needle has done an integer number of rotations, possibly 0. And the other option is that the state comes back to its partner, that is to say, it's done a half integer number of rotations, a half, 3 halves, 5 halves, and so on. So you can then ask what happens to the cat states which were up, plus, and minus down. So if it's a non-net integer rotation, well, each state goes back to itself, so nothing happens. But if it's a net half-integer rotation, then the up state becomes the down state becomes the up state, and therefore the up minus down state becomes the down minus up state, which is minus up minus down. So in other words, the minus state picks up an additional factor of -1. And -1, of course, is e to the I pi. So the phase is pi, and that's where the pi spin glass comes from, and that's where this quasi-energy difference comes from. That's just the pi, which is encoded by this -1. And so the semi-classical diagnostic is you watch this thing over a full period, and then you're going to see whether it's gone around half integer number of rotations or an integer number of rotations. Okay, but what this means in particular is if you start your system not in a cat state, but in one of these states, say the up state, and then you ask, when does it come back to itself? It's not after one period, because it's then inverted, but after 2 periods. So this is period doubling in the pi spin glass. You start with one state, and you only come back after 2 periods. So this sounds extremely underwhelming as far as I'm concerned, because what I've basically told you is if you take a magnet and you rotate it by 180 degrees, you have to do this twice in order to come back to where you started from. So in that sense, this kind of behavior doesn't seem so remarkable. But it is remarkable for the following reason. So this really is a new type of symmetry breaking, because it basically means that your system does not enter a synchronized state at long times. So remember, synchronization was I look stroboscopically and I get a time-independent series at long times. So here you don't get a time-independent series, you get an oscillating series. So the spin points up, down, up, down, up, down after every period. And so this is really something fundamentally new. It's what we call spatio-temporal order. You have spatial order in the spin glass sense and temporal order in the time crystalline sense, because you've got the period doubling. That is to say, your Hamiltonian was time translation invariant under discrete time translations by t, but your states are only time translation invariant after time 2t. So this is the breaking of discrete time translational symmetry by a factor 2. And this is why this thing is called a discrete time crystal, because we only had discrete time translation symmetry to break, but we did break it. And so that's where the word time crystal comes from, the same way that a spatial crystal breaks spatial translational symmetry. So the same way that, say, an antiferromagnet doubles the unit cell of your, say, if you've got a chain and you have antiferromagnetic order, then the unit cell of your magnetic order is twice the size of the unit cell of the lattice. And in that sense, that would basically be a discrete, whatever, spatial crystal. And so here, this is a discrete time crystal. And it's really cool. I mean, as I said, the fact that you have to rotate a spin twice in order twice by half a rotation to get back to where you started from sounds very underwhelming. But it turns out this MBL DTC is extremely robust. That is to say, you can perturb it whichever way you like. In particular, you can take this rotation. You can rotate it by less than 180 degrees. So you basically let the rotating field act for a smaller amount of time, but the system will self-adjust in a way that it always comes back to the half-integer rotation, even if you're trying to drive it away from this, as long as the perturbation is small. So, and even if you have easing symmetry breaking perturbation, the time crystal is still robust. So even though the naive observation, I need 2 half rotations to get back to where I started from, is correct. This is deceptively simple. The system is completely robust against any perturbation that you throw at it. And in that sense, the discrete time crystalline order is not only new in that it's spatio-temporal, but also that it's robust in the same way there's say that topological order is robust against any local perturbation. Okay, so this was really the central results slide about time crystals. Do you have any questions about that?
None in the chat. No, there are no questions in the chat.
Can I ask a question?
Yeah, sure.
There is a question.
Yeah, go ahead.
So this is more of a curiosity more than a thing. So right now, all you required to establish this, at least how you presented, was the fact that your degrees of freedom had easing symmetry. Mm-hmm. If I take some, say, spin 3/2 object, which has, say, 4 sides, each reversed to each other, Can I get like a pi/2 or a pi/4?
Yeah, you can also get pi/3, pi/4, say parafermions. This is not, they don't tend not to have such simple non-interacting pictures, but there is a paper we wrote shortly after this one about parafermionic versions of this. So I can, this by Achilleas Lazaridis and Srijif and myself. So you can do it. It doesn't become any simpler, but it's just possible the same way.
Okay.
Okay. Any other questions?
Yeah, there is a question in the chat now. Is it also not robust to small dissipation terms? So I'm not.
Okay, so no, so dissipation, it's probably not robust against dissipation. It's also not robust against the thing that Hitesh mentioned, that you have a fluctuation in the period of the drive. Right, so it does take the assumptions that I mentioned before, that you have unitary dynamics and that you've got perfect periodic driving. And then, so these you have to keep, but within this, any perturbation of the Hamiltonian is allowed. Okay. All right. Good. All right. So let me just summarize this. So you can basically say, so we know if we've got spatial translational symmetry, we can break that to get a crystal. So we've also got time translational symmetry. We can break this and get a time crystal. But space isn't the same as time, which is why time crystal is a big deal. So basically, to see why this, one aspect of this, so if I live in space, I can go 5 meters to the right, then I can go back 5 meters to the left, and I get back to where I started from. In time, I can't go forward 5 minutes and then go back 5 minutes. And the reason I can't do this is because there's a second law of thermodynamics, which basically tells me there is an arrow of time. So the second law of thermodynamics is what stops you from having these kind of time crystals normally. And what we did is we basically got rid of the second law of thermodynamics by getting rid of thermodynamics. That's what many-body localization did for us. So in a many-body localized system, there's no heat death because you don't thermalize. And then with a periodic driving, you can have this time crystalline behavior, albeit only a discrete time crystal with a subharmonic response. Okay, so one question that often comes up is, isn't the time crystal just the same as the following phenomena? So I've listed those here. And I've been asked many more than that. So they include perpetuum mobile, effective few-body systems, open systems, and also horses. Don't ask me why that person thought horses were a time crystal. But anyway, so perpetuum mobile, I don't have a photograph of one because basically they're not believed to exist, but here's an old drawing of one. So the perpetuum mobile, basically there are two reasons why perpetuum mobile doesn't exist. One is the first law of thermodynamics, the other one is the second law of thermodynamics. So first law of thermodynamics, we're not so worried about. I mean, we just assume that we've got frictionless behavior of our system, and then, it's an idealized setting, but this is not a rare idealization. The second law of thermodynamics is fundamental in this sense, as I explained in the previous slide, and that is people continue to believe that you can't have a perpetuum motion machine for that reason. So effective few-body systems show period doubling very frequently, and this has been known for a long time. I mean, the Faraday waves are an example. Period doubling bifurcations en route to chaos are another example, like parametric resonances or children on a swing are yet another example. So each of these are extremely interesting phenomena. They are not many body phenomena in the sense that the time crystal, which I just showed you, is, but it's important to be aware of the fact that the phenomenology itself is quite similar in these different systems. And if people, so I'm sort of starting to run out of time, if people want an explanation of exactly what the difference is, I'll be happy to answer questions in that direction. Open systems like clocks and lasers are obviously extremely interesting, but I think they don't need to be called time crystals. I prefer to call my wristwatch a wristwatch rather than a wrist time crystal. Okay, so here's the connection to the Majorana fermions again. So I'll be happy to explain. Let's see what else. Okay, now I've got 3 more slides, so I think I can probably get away with explaining this. Okay, so one of the important things, as I just emphasized, about the many-body time crystals, that's a genuine many-body phenomenon, whereas these period doubling things are few-body phenomena. So but there is a very simple relation to an integrable model, which is a Kitaev chain, which I've shown here. So without the, what did I do here? Okay, it seems like I duplicated this term here. Okay, sorry. So basically,
one of the terms was time dependent, right? In your thing.
That's right. That's probably it. Yeah. Okay. Oh, it's probably one is disorder. So never mind. So I did this slide a long time ago. So let me briefly introduce Majorana, stable Majorana fermions, and then explain where the pi comes in. So here's the argument. So if you've got a many-body system, which has got a symmetric spectrum, so that for every state at energy plus E, you've got a state at energy minus E. And then imagine you've got an isolated state at zero energy. Then you can ask, can I perturb the system so that this state goes from zero energy to a finite energy? And the answer is, if there's a gap, you can't. Because if you want to move this state to energy plus E, then from the symmetry of the problem, I must have a second state at energy minus E, but I only had one state to start with, so I can't do this. I need to close the gap in order to move the state away from zero energy, because then I can mix in the other states. Okay, and this is the statement: the mode at zero energy is stable in this gapped system. And this underlines all of this quantum computing using Majoranas and so on. In Floquet systems, you have the statement that the quasi-energy is only defined modulo 2 pi, so that pi is the same as minus pi. Now imagine you've got a Floquet system with the same symmetry. Quasi-energy E goes along with a state at quasi-energy minus E. So then you can make the same argument. If there's an isolated state at pi, and I want to move it up to pi plus epsilon, that is the same as moving it up to minus pi plus epsilon, because they only differ by quasi-energy 2 pi. But then from the symmetry energy to minus energy, minus pi plus epsilon is the same as pi minus epsilon. So in other words, if I move this state up a little bit, I'd need a second state to move it down a little bit, and the existence of a pi Majorana therefore has, it's the same origin as the zero Majorana, except it lives at this point here in energy space. Okay, and so the quasi-energy difference of pi you simply get by occupying or not occupying this particular mode. That's it. And so this is basically the integrable version of this. The integrable version is much simpler. And the cool thing is that this single body picture for the in terms of Majoranas for an integrable chain actually is robust when you go to the many body setting. Okay, so let me conclude with so this was the theory. What is about the experiment for observing an eigenstate order discrete time crystal? So we figured out there are 5 things that you need to be able to do. So one is you need a system where you can realize the phenomenon, and a system where you can observe that you've realized the phenomenon. So you've so this is obvious, but nonetheless you need the same way that in materials physics you need some material which realizes a particular magnetic model. Is the same thing here. Since eigenstate order is there in the entire spectrum, you'd like to be able to probe the entire spectrum. If you've only got a finite size system, you'd like to be able to look at the to look at different system sizes that you can do finite size scaling. And if you've got only a finite lifetime for your system, then you need to somehow find out whether what's limiting the lifetime of your system is intrinsic, so that basically this there is no long time crystal, or whether it's extrinsic, which is if you could do a better experiment, the time crystal would live longer and longer. And so to cut a long story short, what we found is that, or what we proposed last year, or 2 years ago by now, is that if you look at noisy intermediate scale quantum devices, so today's quantum computers, then you can actually check all of these boxes. And I'm not going to go into this in any detail, because I hope that the next talk by Pedram is going to cover much of this one way or another. But basically, so the theory part is there's a prediction of the time crystal, which we made quite a few years ago. And then the plan is to realize this on a nowadays quantum computer. So which brings me to one very important slide. So I didn't do all of this myself. You will not be surprised to hear. So I got into Floquet Systems together with Arnab Das and Achilleas Lazaridis, who were postdocs at MPI PKS at the time, and the work on Floquet periodic Gibbs ensemble and Floquet ETH and Floquet MBL was done together with these two gentlemen. Then Shivaji Sondhi and Vedika Kamani were spending Shivaji's sabbatical at MPI PKS. That's when we came up with the pi spin glass, which was then renamed discrete time crystal. And since then, Matteo Ippoliti has joined Vedika, who's now a professor at Stanford as a postdoc, and the proposal of using NISC platforms was done together with these. And then people from Google and I got involved. So the next speaker, Pedram, is one of them. Xiaomi did a lot of the actual work and doing all the clever implementations to get things off the ground. And Kostya as a theorist at Google who also had input in all of this. Okay, I think that's it. I don't have to go over the summary slide again, so look forward to your questions.
Thank you, Rodrick, for the very, very nice talk. And there were quite a few questions. Maybe in the interest of time, if we have one or two brief questions, we can take. Well, okay, let's see. Are there any questions from the students? From the attendees, rather? Questions?
I have a question.
Good.
So probably in the beginning of your talk, you mentioned level statistics. So you collect. So when you say level statistics, do you mean you collect those Cauchy energies and calculate the statistics of them?
That's right. Yeah. So okay. So that's right. So if you want to distinguish, okay. So that's right. So in a many-body system, generally, so unless you are localized, you expect to have Wigner-Dyson statistics because of level repulsion. So if you take some generic system, then you have Wigner-Dyson level statistics, but then you fold. And if you fold, you're now moving together states which were very far apart from energy, and they can be close to each other. So a priori, they don't repel, right? Because they don't know anything about each other. So if you look here, there's just a folding without any drive actually being added. So you see that there's some very big gaps, and then also some accumulation of states at one particular point. So it turns out if you do this, you simply get Poissonian statistics. Okay, but then if you start driving, you mix them and you get level repulsion, and then you go again to Wigner-Dyson statistics. So that's really the statement. If you look at the eigenstates of your Floquet unitary, they will again exhibit level repulsion, and they will again look like Wigner-Dyson. Right, so that's right. So it's the level statistics in terms of the quasi-energies of the many-body eigenstates of the Floquet unitary.
So what's the horizontal axis for the plot?
Okay, so sorry. So this was really a thought experiment. So you basically it's the same way that okay. So let's go back to this picture here. So here, once you do the band folding, you get a degeneracy here, and as you increase the strength of the periodic potential, the size of this gap grows. So I've done the same thing here. I folded the band so that this picture going from here to there. So each point here is a state folded, but it's zero driving. And now I'm increasing the amplitude of the drive on the x-axis, and increasing the amplitude here just increases the gap. But since here there are many, many states close to each other, I keep mixing more and more states from a bigger and bigger bandwidth with each other as I increase the amplitude of the driving term. Okay, so basically the zero amplitude of the driving is here, and as I make it bigger and bigger and bigger, more and more states overlap, and finally back here I have states coming from all over the spectrum. Right, so basically if I did the same thing for the photonic crystal, I would simply get a gap which sort of grows. What is it? Is it linear? So the gap would grow linearly in the size of the periodic potential.
So, okay. Thank you.
Are there any other questions from the participant? Rodrick, I have one quick one. Maybe we're a little bit over time. It's almost 11:40. But the examples you showed were mostly for one-dimensional systems.
Yeah.
But could you comment on what is being done for higher dimensional systems, or what is the state of
Yeah, okay,
or
so
knowledge.
The problem with high-dimensional systems, you've got interactions and disorder.
Yes.
There's not very many methods to study many-body systems, and so there's basically numerics, but the disordered system, doing numerics and extrapolating them to the thermodynamic limit. If all you can do is like order a few times 10 spins, doesn't get you very far, whereas at least in a one-dimensional
that part I understand.
Okay,
but
so
conceptually there is no, like, for example,
conceptually there's no
MBL,
difference.
I'm not entirely sure, does it exist in 2 dimensions? Like,
so many body localization is generally not believed to exist in 2 dimensions. But that doesn't mean that it may not exist on phenomenally long timescales.
I see.
Conversely,
right.
Not everyone thinks that many body localization exists in 1 dimension, but it's clear that it exists on very long timescales.
That's right. Yes,
yeah.
I have seen papers in that.
Yeah,
I see. I know what you're talking about.
That's right.
The system sizes to argue that are very, very small.
Yeah, that's right.
Okay. Sure. So yeah, it is 11:40. If there are no more questions, we should thank Rodrick again, and thank you, Rodrick, again for a wonderful talk. And we will
thank you.
Meet in I believe 20 minutes. And as Rodrick mentioned, Pedram Roshan is the next speaker who will tell us about all the cool implementations of this stuff on quantum computers. So with that, we'll take a break and see each other. We'll see each other in 20 minutes then. Thank you. Thank you, Rodrick, again. Yeah.